Welcome back. This is the day Lord's made. Let us rejoice and be glad in it. In this video, I'm going to talk about series and parallel circuits. This will be a follow-up to my last video. So, and first off, a circuit is just a way to describe, a circuit is just the way electrons move through wherever it's going. All right, it's basically like this idea that the electrons have a path they're going to take, and the circuit is just talking about, hey, here's where they're going through. All right, so there are series circuits and there are parallel circuits. So a series circuit, in series, everybody has to go the same way. So here we have a battery, which again provides some motivation for electrons to move. And the electrons are going to move along through this circuit. And then they're going to go through a resistor we have. I just picked a light bulb, but again, a resistor could be anything in the way, anything that's using energy off the line. You know, hair dryer, computer, whatever. All right, so in series, the current is the same everywhere because the electrons only have one path. In fact, if you have a break in the circuit too, then what happens? So we'll break the circuit. So we break the circuit. There we go. Oh no, the circuit broke. All the electrons stop moving. Because in series circuit, if they can't take this path, it's done. There's only one path. So this is a series circuit. In parallel circuitry, electrons get a choice. So all the electrons take off, they're going through the circuit, and then they get here and they get a choice. They can either go to the top path or they can go to the middle path as they try to get over here. Again, the electron's goal is to get to the positive end. So they leave this side here, leave the negative end, going towards the positive end. So when they get here, they make a choice. Since both are the same resistance, the electrons don't care which way they go, and so they choose them equally. And so we can see the current is the same for both of these. All right, the total current's larger though. So comparing a series versus parallel, even though this one has twice as many resistors on it, this series circuit only has one resistor, this one has two. But even though it has two resistors, we still get twice as much current because in parallel, they don't compete against each other, all right? In series, this is, think of it like if the college has one major, so the resistor is the major, all right? So people out in the world that want to get an education could choose this college, but they only have one option. They would have to choose this one. So it draws a certain amount of current, a certain amount of people. College 2 over here, the parallel one, actually has two options. What does that mean? It's going to draw twice as many people to it because it has two different viable paths that people could take as they work on their education. All right. So, but the current doesn't have to be the same everywhere. You'll see that here, the total people, 2 amps is different than the paths over here. There's only 1 amp in both these paths, but there's 2 here. In series, it's 1 amp everywhere, but here it's 2 amps in this location here, and then 1 amp here. This would be like everyone's taking a class and it's required. So these would be like the general electives. Everyone needs to take this class, and then you spread out to the actual major you want. All right. Now we could get different amounts of current if they were different resistors. So if all of a sudden we make this resistance larger, what's going to happen? Well, because this is a larger resistor, then this one less people take it, which is just saying that, well, if at high school, when you're choosing your classes, the classes that are harder, people don't take as much. All right, they're going to choose against it. All right, so less people sign up for AP Calculus, AP Physics, than sign up for maybe another class that might be easier. Okay, so for parallel circuitry, when the electrons change and the current isn't the same everywhere. So there's different amounts of electrons and different paths. Now, with the series one, if we broke it, everything shut down. But in parallel, if we shut one down, what happens? Well, sure, we don't get anybody taking this one, but we still have this other one, which is no different than saying back to our original analogy, if a college offers more than one major, if all of a sudden this major no longer exists and it's no longer an option, people still come to the college because, hey, there's still another major that they can take, okay? Some other big differences too between series and parallel is, again, this idea of how the resistors add up. So in this first one, the top left one here, we have one resistor. If I add a second resistor, what happens to the current? It goes down. Why? Because when we add these two together, we get twice as much resistance. 9 ohms plus 9 ohms makes 18 ohms. The amount of current is equal to the voltage divided by the resistance. So we have 9 plus 9 is 18. 9 divided by 18 is a half. And so the current here, we don't get a half amp. Up here, we had 9 divided by 9, that's 1. So when you add resistors into series, you get less current because every time you add another resistor, you're making that path more challenging. All right, so if we decide to add another one here, so let's go ahead and add another resistor. We just said, hey, the requirements for graduating just got harder. All right, who wants to sign up now? All right, I didn't want that big resistor. 1 second. Get rid of you. So the smaller light bulb, there we go. This is what I want. Turn around. There we go. Okay. Well, if we add another resistor, what happens? The current drops even further, because in series, every time we add a resistor, we're adding another requirement, which makes it you're less motivated to take it again. The voltage is how motivated you are, and all these resistors are anti-motivation. So every single time we add another requirement on, you're less motivated and less likely to take that path. So every time we add one, it goes down. Now for parallel, if you add another resistor, they don't add up. Adding another resistor actually adds down. It actually makes another option, and so the actual total resistance goes down. So if we say, hey, you know what, we're going to add a new major here. All right, we're going to add a new major that people can choose to take. And so they can choose to take this path instead. So here we go. What's going to happen? We have 1.5 amps right now. Now we have 2.5 amps. We got more current. By adding actually another resistor, we actually get more current moving through a parallel one. And so the math for this is a little more tricky. The math for adding up resistors in parallel is actually 1 divided by the resistances plus 1 divided by the resistances added up until you get 1 divided by the total resistance. So here it just adds them straight. R plus R plus R, that's 9 plus 9 plus 9, that's 27. All right, let me make these numbers a little smaller here for us. Back to the same. So what's the equivalent resistance of these ones here? Instead of taking 9 plus 9 plus 9, making 27, it's 1/9 plus 1/9 plus 1/9. And what does that add up to? It adds up to 3/9. Flip it over because it's 1 over the resistance. This would be equivalent. This looks like a 3 ohm resistor. All right. These things here collectively look like 3 ohms. 9 divided by 3 gets us 3 amps. Again, the equivalent resistance is a little tricky. The idea is that when you add another resistor, it's going to make it get easier to get through the paths actually, because again, it's a parallel part. So for quick calculations, if they're the exact same resistor, like 9 and 9, so let me go and take this one off here. If you just have 2 9 resistors, then it's 4.5. You just divide by 2. And so here we have 3 of them. We divide by 3 if they're all the same. So if we have 3 9 ohm resistors in parallel, then the actual resistance of these 3 is 3 ohms. Okay. All right, next thing I want to talk about is voltage drop. And to talk about voltage drop, I'm going to talk about it just in series. So I talk about it in parallel. So I'm going to go ahead and get rid of these ones here. Oh, we just have to put them. Okay, here we go. So voltage drop is the idea that as electrons go through a path, they get demotivated and lose some motivation. So if you just have one resistor to go through, you're going to spend all your motivation going through that one. So here we see that the voltmeter says 9 volts. What it's saying is going from this part here, this point here to this point here, it lost 9 volts of motivation. Going across a place with no resistor costs nothing, which is basically saying as the electrons go through your copper lines in your house, they don't lose any energy moving through that because it's a conductive path. It's just like, oh, sure, I'm just moving here anyway. It's not going to cost me anything. All right, it only costs you motivation when you do an assignment. Now, if you have one assignment to do, you spend all your motivation on that one assignment. You wake up for the day, got one thing to do, all of it goes there. But if you have more than one to do, then you got to save some energy for the other one too. So let's go ahead and put another resistor in here. And this is in series because everyone's got to do 2 assignments now. All right, so now you still have the same motivation. You got the same good night of sleep that you had before, but now you got 2 to do. So when you go across these places here, what's going to happen? You got to save some motivation for each resistor. So you have 9 volts of motivation, 2 assignments. You're going to spend half your 9 volts on each of these. So we'll spend 4.5 volts there, and then going from the next one, we're going to spend 9 volts going from here to there. All right, again, we're not spending any motivation going across just the copper wire itself, only when you go through a resistor. Now the total drop adds up to the total battery. So we had 9 volts of motivation going from this place here to this place here. We're going to spend all of my motivation going through there, but we're only spending half it for each one. Now, you probably don't just have 2 assignments. You might have, oh no, like 3 assignments. Here we go, another assignment here for us. So what's our motivation drop now? So we have 9 volts to spend. We got to do 3 assignments. All 3 assignments are equally hard. So we're going to proportionally spend my voltage through these things here. All right. So this is 1/3 of the total resistance, which means, because it's 9 of them, they're all the same. So this is 1/3 of a total resistance. So we're going to spend 1/3 of my voltage going across this one here. So we'll get our voltmeter out and see what the voltage loss is. Look, it is 3 volts. We spent 3 volts going from here to there, which is to say, I woke up with the day with 9 volts of motivation. I'm going through the path. I get to the first resistor, and I see that I have 3 assignments to do. They're all the same. I'm going to spend 1/3 of my motivation going across this one here. All right. And then I would spend 3 volts going across this one. And then I would spend the last 3 volts going across this one. So I saved and spent equally for every one of them. Now, what if one of the resistors is larger? So this one's going to be twice as big now. We have one that's twice as resistive. What's that going to do to your motivation? Well, it's going to use twice as much of your motivation. All right, it's going to be reducing by that much. The way to figure this out is you got to figure out the total resistance you're going through. We're going through 9 plus 9 plus 18. That adds up to 36. We're going to go through a total of 36 ohms resistance. This 18 ohms represents how much of it? 18 out of 36, this represents 1/2 of the total resistance you're going to go through the day, which means you're going to spend half your motivation. So you're going to have 9 volts of motivation going across this first path. It's going to cost me half of my 9 volts. So, and since this represents half of the total resistance, as we go through the whole circuit, I spend half my voltage. These ones here now, this is 9 out of 36. It's going to spend 1/4. It's 1/4 of the resistance. So I'm going to spend 1/4 of 9 volts going to that one. So to find a voltage drop in series, what you do is you add up all the resistors. All right. So we got 9 plus 9 plus 18. Then you find out how much that resistor individually brings to the table. So for this one here, the total resistance was 36. This one brings 18 of it. You're going to take the resistance that this one brings, the individual, divided by the total. So 18 divided by 36 is 1/2. You'll take that number, multiply by the battery, what it's providing. We're going to get half of the 9 volts. Let's do one more. Let's bring these numbers together. How small can we make these things? Oh, good. We can make them real small. All right. All right. We're going to calculate the voltage drop for these 3 light bulbs. These 3, so again, think of these like as things to do. The electron is going to take off. They got 12 volts of motivation. They're going to go through a 2 ohm resistor, a 3 ohm resistor, and a 1 ohm resistor. We're going to find out how much motivation they lose going across each one of these things here. All right. So to find the resistance, to find the motivation lost here, we take this resistor, which is 2, divided by the total. So the total is 1 plus 3 plus 2, that makes 6. 2 divided by 6 is 1/3. We're going to take that 1/3, this represents 1/3 of the resistance times the motivation. So we're going to get 1/3 of the 12 volts. So again, you woke up, got a good night's sleep, you got 12 volts of motivation, you're going to spend 1/3 of it here. What's 1/3 of 12? That is 4. We're going to spend 4 volts going across this one here. The next resistor, this is 3 out of the 6. So it represents 1/2 of the total resistance. So we're going to spend 1/2 of 12, which is 6 volts. The last one is 1/6 of the total resistance. And so we're going to spend 1/6 of 12, which is 2 volts. All right, so big idea for series to find the voltage drop in series, it's all proportional. Just how much motivation do I have total, how much of the resistance comes from this resistor, and then you proportion it out. But again, it's no different than saying when you're working homework assignments, you got to save motivation for every single part along the way. Godspeed.